So, good afternoon, all of you. I know it's an afternoon session, so most of you are feeling very sleepy. But I would like to request your contributions and but concentration towards the session because I'm taking the contents as much capsule form as much as in a capsule form for the better understanding and deliver it to you. Okay. So I'm going to discuss about the concept of support vector machines, then linear regression, and then we are going to have a hands-on implementation of classification techniques, a regression technique, as well as a uh, clustering technique. Okay, so hope you have now got the idea regarding how clustering works, what are the different types of clustering and all. So we are going to implement the k-means clustering with a particular data set. And along with that, we are going to implement the linear regression and the support vector machine classification. Okay. So before getting into this session, I would like to share a link with you. I want all of you to download the content I have shared with you. I'm pasting it on the chat box. Okay. So all of you, please download it and keep it unzipped. Okay. So we are carrying out our experiments on Google Colab. Are you able to download it? Please be interactive as we did in the previous sessions. Okay, then only it will be very fruitful for you. And if you have any doubts regarding any of the points I'm discussing, please let me know, then we can discuss it on and make it clear. Okay. So are you able to download it? I'm not getting any response from here. Please be able to download.
Yes, sir.
So I'm sharing my screen. Okay. So when I ask you something, please feel free to respond after unmuting your mic. Okay, no issues. And so hope you are all able to download the files. Okay. Now, before getting into the concepts of the classification, regression, and the clustering techniques, you have already done with the clustering. I'm discussing a little bit about the classification and regression technique. Okay, I'd just like to give you some essential math to understand the concepts. Okay, so first of all, I would like to ask you, what is the equation of a line? What is the equation of a line? Can anyone unmute and say, what is the equation of line?
Y equals mx plus c.
Yeah, y equal to mx plus c. And what is the geometric shape represented by this equation? Ax plus by equal to c. What is it actually? No. This also represents a line. Okay, this also represents a line actually. These two representations are actually equal. Let's see, like ax plus, let this equation be mx plus a. Okay, so ax plus by equal to c. What will be by? It is minus ax plus c, right? And what is y? Y is equal to minus a by b x plus c by b, and I'm naming it as M, that is minus B by B, sorry, minus A by B as M and my C by B as K, then the equation becomes y is equal to mx plus K. So, first of all, you have to understand that these two representations are equal. Okay, y equal to mx plus ck and ax plus by equal to c is both represents the equation of a line, and this is the slope and intercept form, and this is the Cartesian form. Okay, so now you know y equal to m x plus. Okay, so what is this m? What is this m? Slope. Yes, exactly. Y is m is slope, and what is this k? Constant. No, actually, it is called as intercept. Okay, minus. Okay, so now what is the relevance of, or what is the significance of this m and k? What will happen if you change the values of m and k? What will happen? Do you know what will happen when you change the values of m and k? Okay, I will show you an example. Okay, see, this is a tool called desmods.com. Okay, so here y equal to mx plus k. Okay, and I'm first I'm putting a value for m as 1 and k as 1. Okay, so now the equation is like, what is the equation? This y equal to, so y is equal to x plus 1. This is like y equal to x plus 1. Okay, so this is the line. Fine. So y equal to mx plus k with m equal to 1 and k equal to 1 is actually representing a line, right? Now you see, if you change the value of m, what is happening actually? What's actually happening? On changing the value of m, you can actually rotate the line above the y-intercept. Okay, clear? And what will happen if you change the value of k? We will get a freedom to move upwards and downwards, right? Is that clear for you? What is the significance of m and k? Now, suppose you have 2 points. See, 2, 3 is a point. Okay. And I'm sure giving another point like 5, 6 is another point. Okay. So you can see 2 points. So how can you actually make the line y equal to mx plus k exactly pass through these 2 points? How can I do that? I can just adjust the values of m. I can adjust the values of m as well as adjust the values of k. Then at c, k equal to 1 and m is equal to 1. Okay, the line passes through exactly the points 2, 3 and 5, 6, right? Is it clear for you? Okay, so in the case of 3 points, what if in the case of 3 points, like in between, telling you 3.5 or 3.4.5. So there will be another point, right? There will be another point. Okay. So somehow we can adjust these 2 points, these two values, and we can approximately pass through all these points, right? There will be some errors, but we can approximately pass through the distribution of these points. Okay. So finding out a line passing through or approximately passing through a set of points is actually the task of finding the value of m and k, right? If you want to find a line which passes through some or which is approximately passes through a set of points, then you have to adjust the value of m and k in such that we have to make this line pass through all the points approximately, right? So finding a line means, what is the task? Finding a line implies find the values of m and k. Is that clear? Is the idea clear for you? Are you all sleeping? Okay, fine. So please feel free to ask if you have any doubts at any point. Okay, I'll be happy. I'm very happy to explain it again. Okay. So if you have any doubts, any confusions, please feel free to ask. Okay. So now we can move to the concept of regression. Okay. So here we are going to discuss about a particular machine learning algorithm called regression. So you might discuss about this regression in the morning session. So is regression a machine learning task, a supervised or unsupervised task? What is it? Is it a supervised or unsupervised task? Machine learning regression. It's a supervised learning technique. So as you discussed in the morning session, you can see for classification, the outputs are nominal, but in regression, the output is actually continuous. So we have a set of independent variables. Okay, we have a set of independent variables and a dependent variable. Okay, so we will have a set of independent variables x1, x2, x3, x4, x4, etc. up to xn, and there will be a y value. So in both classification and regression, the representation is same, but the actual difference is in regression the y is actually continuous. The value of y is actually continuous. Okay, so we need to find. So what we have to do is we need to find an f, a function that maps x1, x2, etc. up to xn to the value y, to the value y. Okay. So regression is actually a kind of function approximation. Regression is actually a kind of function approximation. Okay. So there are several type of regression algorithms exist, and among them the most simplest and widely used regression technique is actually called as linear regression. What is it? Linear regression. So linear regression is nothing but fit data with the best hyperplane which goes through the points. Okay. So there will be so this is an example of a simple case, that is we are having one independent variable and a dependent variable. So according to the change in the value of the independent variable x, we will have a change in the value of dependent variable y. So in this example, there are different points which represents each xy. Okay, each xy. So the distribution of this data need to be learned using this slide. Okay, so here we found a line which approximately passes through all the points, but the actual thing is we can find several lines. See, I so if you look into this, you will found that you can actually find some other possible lines which passes through all these points, right? So there will be several lines that we can approximate the points. Okay. So what is the best line? What is the line we need to choose? For that, you need to understand that after fitting a line, after finding out a line, you can see for the for this value of x1, okay, we have a particular value for y1. For this value of x2, we have a particular value of y2. Okay, but after fitting this line for this x2, if you see this x2, you can see for this x2, the line is approximating this to this point. I'm calling it as y2 cap. So there is a difference, there is an error between the actual y value and the approximated y value, which is called as the residue. Okay, which is called as the residue. Okay, so there may be a possible residue for all of this point. The first residue is actually y1 minus y1 cap. The second residue will be y2 minus y2 cap. The third residue will be y3 minus y3 cap. Okay. Likewise, we can have n points, that is yn minus yn cap. Okay. And the total error or the total residue can be calculated by summing up all these stuff. Okay. Summing up all these stuff. But just think what will happen if you have an error of +5 and you have an error of -5. What will happen? In total, the error will be +5 plus -5 equal to 0. Does that means we are not having any error here? No, right? So what we have to do is to calculate this error. To calculate this error, we will take like y1 minus y1 cap whole square plus y2 minus y2 cap whole square set up to yn minus yn cap whole square. Okay, so we will get rid of all the negatives. After that, we have to take this square root. So in total, the error in a regression can be represented as y error can be represented as root of sigma yi minus yi cap whole square. So this is the total error. So we have to find a line in such a way that the total error produced by that approximation should be minimum. The total error produced by that approximation should be minimum. Okay. So have you got the idea? Is that clear for you? How regression works? Okay. Now our task is, so in this case, you actually got how to find out the line. Okay. So in this example also, you have a single independent variable x and a dependent variable y. A single independent variable x and a dependent variable y. Okay. So you have to find a line y equal to mx plus k, and I'm representing it in another way, beta 0 plus beta 1x, where beta 0 is the k intercept and beta 1 is the slope. Clear? And for this particular example, the data given to you will be like, there will be an x column, there will be a y column. Like for this x, you may have 1, 1.5, 2, 2.3, 2.8. And for this y, you can have 1, 3, 5, 5, 6.7, 8.2, like this. Okay. So to find out the value of beta 0 and beta 1 from this data, what you need to do is, there are 5 observations. So the value of n is equal to 5. You need to find out the column xy. Okay. Then you need to find out the sum of xy, then sum of x, sum of y, then sum of x square, sum of x whole square. After substituting the values of all these summations, we will get the value of beta 1. And similarly, using beta 1, sigma x and sigma y, and then you can also find beta 0. So finally, using these equations, you will get a beta 0 and beta 1, and you definitely found the line beta 0 plus beta 1 x. Okay, so this is how usually we solve the problem of linear regression. Okay, now just see, consider an example, a real time example. Like you have an independent variable x, which is represented by time spent for studies. Okay, and y is the mark obtained for exam. So maybe like daily, if 5 hours a day, he may get 95%. If he spend 4 hours, he may get 92%. 3 hours a day, he will get around 80%. The 0.5 hours, he may get around 88%. Okay. Likewise, we will conduct a survey and find out the amount of time a student spent for studies and what the percentage mark he got for the previous exam. Okay. So here we have an independent variable and a dependent variable, and we are establishing a relationship that the mark of a student can be predicted using the amount of time he spent for studies. So on visualizing, you can see the time can be in x-axis, the corresponding mark will be on the y-axis. Okay. So on plotting these points, you may get some interesting facts. Okay. So you can see the dependency of time on mark is actually a quadratic in nature or a linear in nature. Okay, you can find like this. But in a real-time situation, is is the, is only the time spent for studies contribute to the mark obtained by a student? What do you think? Can anyone say some other factors which influence the mark of a student? First one is time. The other one can be, any guess? There are situations even if a student spend a lot of time for studies, he will not get any marks, right? So some other factors may be influencing that. What is it? We can say an IQ level of the student, right? Do you think it's right? IQ level of a student. Okay. So the Y should be marked. So how will you visualize this thing? Actually, we need to have an X1, we need to have an X2, and the Y can be marked. So if you plot the data here, okay, if you plot the data here, the mark obtained by the student along with his IQ value and the time spent for studies, okay, the data points will be distributed over a space. So with a single line, we cannot actually approximate this, right? We cannot actually approximate this. So what we can do is, instead of a line, we will somehow approximate a plane. Okay, we will somehow approximate a plane. So what is the equation of a plane? That will be like y equal to beta 0 plus beta 1 x1 plus beta 2 x2. So that is the case of if we are having two features and a target variable. Okay. So similarly, in some real time situations, we may have n number of independent variables and a dependent variable. Okay, n number of independent variables and a dependent variable. So in general, for a situation, for a context, we can see there will be x1, x2, x3, etc. up to n independent variables that maps to a dependent variable y. So the equation or the hyperplane, if it is in the case of a 2D plane, it will be a line. Then if it is in the case of a three-dimensional space, it will be a plane. And if it is more than 3 dimensions, then we will call it as a hyperplane. So the actual thing happening behind the regression is we have to find a hyperplane, okay, that maps the variables x1, x2, etc. up to xn to y. Okay, so that hyperplane can be represented by beta 0 plus beta 1 x1 plus beta 2 x2 plus etc. up to beta n xn. So the ultimate task, our task of doing regression is to find the vector beta 0, beta 1, beta 2, etc. up to beta n, which is represented as beta cap. Okay, provided you will have x1, x2, etc. up to xn. Okay, x1, x2, etc. up to xn. So this can be considered as a matrix, right? So this is represented by x and a target variable y. This is a column matrix y. So ultimately, we need to find the vector beta cap from the vectors from the matrix x and the column vector y. So how can we find that, right? Because this equation only works for a single dependent variable and a independent variable. Okay. So in general, the case of a multivariate regression, we have to find out beta cap provided with x and y. The inputs are x and y. We need to find a beta cap from here. So beta cap can be calculated as beta cap is equal to x transpose into x whole inverse into x transpose into y. So we can find out the beta cap. Okay. So this is exactly happening in multivariate linear regression. And actually, this is the internal working of the regression technique. You need not to bother these stuff because we can do or we can implement linear regression using a single function call. And but it is essential to understand. It is essential that you have to understand the concept of linear regression. Then only you can actually transform or model your real-time situations to a linear regression problem. Okay. So apart from linear regression, you can also see that there are different type of other distributions where linear regression won't work. Okay. So in this case, see, the linear regression or the linear approximation is not appropriate. We can approximate it using a parabola or something like that. Here also there will be some outlier kind of stuff, so these won't work. And here also the presence of outlier is actually uh, making errors in the like approximation of the function. Okay, so there are several situations we need to handle, and we have to choose some other regression techniques apart from linear regression for this task. Okay, so this is the end of linear regression, and this is a very abstract introduction, a very abstract explanation regarding linear regression. Hope you got this. Do you have any doubts? Have any doubts? If you are clear with the concepts, please put an S on the chat box. Or if you have any doubts, please feel free to ask, and you can unmute and ask actually. So hope you have downloaded the attachment I have shared with you and unzipped it. You can see a file called day 4, and within that you can see 3 folders: classification, clustering, and regression. Okay, classification, clustering, and regression. So you can open this regression folder. Okay, so you can see an insurance.csv file and a regression.ipynb file. So I have again shared that link to the drive in the chat box. If someone is still okay. So upload this to regression.ipynb, and after that you can upload the insurance.csv. Okay, so I'm doing that. A Google Colab. Within Google Colab, using this option. Okay, using this upload option, you can upload it. In my case, it's already there, so I'm opening it regression.ipynb. So you can see a file like this. Okay, you can see a file like this. Then after connecting to Google's cloud server, after connecting to Google's cloud server, you can upload the CSV file, insurance.csv file, on the local memory available for us, insurance.csv. Okay. So you can see the insurance.csv is now uploaded. So hope everybody is at this point. Okay. So could you please put an S on the chat box if you are okay with uploading the notebook file as well as the data file. If you have done this, please put an OK or an S on the chat box, or even you can unmute and say yes. Only 4 responses. I want around 15 responses. Then only I can do. I want to ensure you people are doing it. Okay. So if you have done with uploading the notebook file and data file, please respond to the chat. Yeah, only regression is needed. You can also upload the data. Okay. To upload the data file, you can click on the left side. So see on the screen. On the left side, you will have a folder file. Okay. And in that folder file, there will be an upload option. From that upload option, you can upload the insurance.csv. Okay. Jumana, are you getting this? Are you able to upload the file? Hi. So people are responding now. Now, first, what you have to do is, so that's not an issue. You can upload, still upload. It says if you exit from the Google Colab, the file will get removed. And if you try to run it again on this Google Colab, you have to upload the file again. That's it. Okay. Yeah. So you have uploaded the file now. Now, first thing you have to do is in the edit option, clear all input. Okay. In the edit option, clear all inputs. Clear all inputs. Fine. Clear all input. Is that okay? So we can now implement it. See, first of all, we are importing all the required packages, that pandas, numpy. Yeah, clear the output. On the edit file, you can see clear all outputs. On the edit option at the end of the menu, at the bottom of the menu, you can see clear all output. So we are importing pandas, numpy, matplotlib, and seaborn. Okay. So hope you are all familiar with pandas, right? On the first day itself, we have discussed about pandas, right? Yes. So we have imported everything. Now see, we are reading or loading our insurance.csv file to a variable called metadata and printing its header. So you can see on printing, there are several fields: age, sex, BMI, children, smoker, and region. Okay. So from this, we have to map to an insurance charge. Okay. What is the insurance premium for this particular person? Okay. So from this example, we have to understand that the insurance premium charge depends on the age, sex, BMI, children, smoker, and region. Okay. Because if someone is on higher age, okay, someone is on higher age, what will happen? The premium may be higher, or otherwise the premium may be lower. Okay. sometimes for the gender, females and male, there may be a difference. And for the BMI represents the healthiness of a person. So if BMI is very low, there may be a risk and the charge may be high. If have children, there may be some claims and all. So that also depends. Then if the person is a smoker, that also contribute the charge. And where he lives, if 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 a person lives in a terrorist place or something like that, then there will be a high risk for giving a giving an insurance to that person, right? So all these factors affects the value of premium, okay, insurance premium charge. So we have to find out a model, a regression model that maps all these factors to charge. Okay. So on printing this head, you can see see the data itself on describe on calling the describe function. You can see the statistical features or the statistical parameters of the uh, numerical fields. Okay, you hear the age, BMI, children, region. Sorry, children and charges are the numerical data. The sex, smoker or not, and the regions are actually the categorical values, right? So we will get the statistical values or the parameters of all the numeric columns here. Okay. Okay. Now, so you got the statistical parameters like count, mean, standard deviation, minimum value, quartile, 25% quartile deviation, 50%, 75%, and maximum values. Okay. Now we can just analyze this data before applying the regression values. That is, see, we are plotting a bar plot with X as female, sorry, sex and Y as charges. Okay. So on this, see, for male, the average charge, the female, the average charge will be around like this. And for male, the average values are around 14,000. Okay. So this is for just for the sake of interpretation, for the visualization purpose. There is nothing much with visualization for the regression task. This is just to understand about the data. Okay. Now we are just box plotting the different features like sex, okay, like charges, then focus, okay. So you can see the average value of female candidates, okay, who are smokers and non-smokers. Okay, so for smokers, the premium charges are high, and for non-smokers, the premium charges less. Okay, for the males also, for the smokers, you can see the premium charges are high, and the uh, premium charges are low for the non-smokers. Okay, and also we can have a distribution plot. Okay, distribution plot for this. See, so from this distribution, we can see the average premium is around 10,000, and rarely it will move to around 50,000. Okay, so these are three different type of visualizations we can do with this data to interpret something. Now, what we are going to do is we are trying to build a regression model. Okay, for that, see, first we have to convert the non-numeric fields, that sex, region, and smoker, to numerical values. For that, we have to use a package called label encoder. Okay, so in label encoder, see, we are importing label encoder from sklearn preprocessing, and we are importing it. Then we are creating an object. Then the metadata dot of sex is actually transforming to numerical values here, and metadata of region. Okay, and metadata of smokers. And after encoding these columns, you can see the sex is now mapped to 0 and 1. Okay, the smokers are again mapped to 0 and 1, and the region is again mapped to 1, 2, and 3. Okay, 0, 1, 2, and 3. Okay, is that clear? Now our data is entirely numeric in nature. Now this is the x, right? As I said, for doing the regression, these columns are the independent variables, and this is the dependent variable. So this is what we have as the input. So these values can be considered as the x. Okay, from age, sex, BMI, children, smoker, region are actually the value of x, and the charges are y. So first we have to split that into x and y. Okay, first we have to split that into x and y. For that, we are using the ILO function. We have to take all the rows and take the columns till the second last one, and we have to take the last column as y. Okay, so on doing this, you can see x's, the features they see 19, 0, 27, 0, 1, and 3. Okay, and this is the charges. Okay, you can see the values of x and y. Okay, are you getting this? Are you okay with this till the point what we have discussed? Are you able to run it? So we have prepared our x and y. Okay, so we have x and y now. Now what we have to do is have x and y. Now we will split this x and y into two parts. This is called x test, sorry, x train, and this is called y train. This is x test, and this is y test. Okay, so after building the machine learning model, okay, after building the machine learning model, we will give X train and Y train for training this. Okay, so after training, we will get a predictor, okay, a predictor, and we will give the input X test to predictor, and we will get a Y predict as the output, and we will compare this Y predict and Y test to find out the accuracy of our model, how much it is correct. Okay. So for splitting that, we have to use a function called train test split. Okay, train test split. So on train test split, you have to give the x by the test size. Okay, we need to have 2% test size. That is, if we have 100 documents, 100 observations, 80% should be taken for training, and 20% should take for testing. Okay, so 0.2. Then the random state is for randomly choosing the values of x and y. Okay, so after applying train test plus split function, we will get x train, y x test, y train, and y test. Okay. Now the next step is we have to create the object of regression, linear regression. For that, import scalar dot linear model, import linear regression. Then model is equal to linear regression of. Okay. Now, for training, we have to call the fit function with x train and y train. Okay, with x train and y train. Now to check the correctness of our model, what we are going to do is we have to call the score function and we have to give X train and Y train. So it will give a measure on how much the X train value predicted to Y train. Okay, how much correctly it is predicted. Also the X test and Y test. Okay, so we can run that part. Okay, so you can see the R squared value. This is called the R squared value. The the linear regression model is completely or 100% accurate if we get a value of 1 for this R squared error. But now it is only 0.74, so there is some error. And for test data, we have 0.78. So to check the correctness of this, you can plot this. Okay, we are plotting the Y train and Y predict. Okay, Y train and Y predict on the Y predict. Y pred is actually the prediction on giving X train to the model. So if it is so you can see some errors at this point, right? So this is the difference. Okay, this is the prediction difference in the prediction, and this led to the error. Okay. Similarly, you can apply this for test data also. So the actual data is actually in blue color and the predicted values are in orange color. Okay. So if it is 100% accurate, what you can see is these two orange and blue curves or the blue lines will intersect. Okay. So we know that with linear regression, the approximation to this particular problem is actually 74% correct for the training data and 78% correct for the test data. So what is our solution for this? Because around 30% error is there. So we can try with some other regression models available in sklearn. So another regression model is there, random forest regressor, and it is available in sklearn from sklearn.ensemble import regressor. The only difference is the change in creating the object. Here the model is equal to linear regression and here the model is equal to random forest regression. Everything else is same. So we can try with this tool. See, so with random forest regression, the accuracy, the correctness become 97.97% for the training data and 89 point for the 86 point for the test data. Okay, so the plot of that model, that is random forest regression model, is actually plotted here. So on comparing this and this, you can see the errors are bit lesser in this case. Okay, so the random forest regression is more better than linear regression. Okay, so now we are going to have a very brief and very quick discussion regarding the support vector machine algorithm, which is a classification algorithm. This can also be used for regression techniques. Okay, so as you discussed in the morning day session, like machine learning is classified into supervised, unsupervised, and reinforcement learning. And in supervised learning, we have the labeled data, that is, we have the inputs as well as the output. And the prominent techniques in supervised learning are classification and regression. And for both aspects, we can use support vector machines, but mostly or widely it is used for the classification task. Okay, so as you can see in the slides, SVM is a supervised learning method that looks at data and sort it into one of the two categories. Okay, so basically the classification techniques are performed for two classes. That is, for a given data, we have to predict it belongs to one class or another class. Those type of classification techniques are actually called as binary classification. Okay, binary classification. The others, if you have multiple classes, like a given input belongs to a fast learner or an average student or a slow learner. Okay, so then it will become more number of it is having more number of classes, that it become a multi class classification. Okay, multi-class classification. So I am explaining the concept of support vector machine with the binary classification, and it can be simply extended to multi-class problems. Okay, so as you can see in the example, we have two different training data. One is labeled as strawberry and one is labeled as apple. So after training the model, we will get a prediction stuff, and on giving an unknown new data to the prediction model, it will get predicted as a strawberry or an apple according to the features given to it. Okay, this is exactly what is happening in support vector machine. And now we can discuss what is the internal mechanism we can uh, have in the support vector machine classifier. Okay, so here we have the labeled data, then we are actually finding a decision boundary. Okay, on plotting the data, okay, on plotting the data, we can see the plot, the data of one class clustered in one side and the other class clustered in another side. And in most of the cases, we will be able to find out a line that passes through these two group of data. Okay, so after finding this line, and which is called as a decision boundary. So if a new data comes and if you plot the data in this surface and it comes under this line, then we can say it is a strawberry, otherwise it is a apple. Okay, so this is the underlying mechanism of SVM, and we can explain or we can have this particular situation with an example of, see, there are a set of there are the details of a set of students, female students. Okay, see their weights and height, and male students, their height and weight. Okay, so for male students, see the heights are from 179 to 187, and here 174 to 185. And the weight is actually, the minimum weight is 65, the maximum is 88 here. And but in this case, the minimum weight is 72 and the maximum weight is 90. Okay, so on taking this data on x-axis and y-axis, you can see the girl students will be clustered over here, and the female students, sorry, male students will be clustered over here, and the female students will be clustered over here, because they are having less weight and less height, but the male students are having more height and more weight. Okay, so if you have the height and weight of a new student, we don't know whether it is a boy or a girl, but there's a new student, then how will you decide where this new students belongs to? Okay, new student belongs to. So for that, we can actually find out a hyperplane that separates these two data, right? This is a hyperplane, but this is also a hyperplane. Okay, so according to this hyperplane, this is the class, that is that new student belongs to the boy group, and according to this hyperplane, the new student belongs to the girl group. So what will happen? Okay, what can we do for this? What we can do for this is we have to find out a line with a criteria that we need to have a maximum marginal distance. Okay, we have to have a maximum marginal distance. Marginal distance is nothing but it is the two it is the distance between two lines, which is called as margins. Okay, distance between two lines, which is called as margin, that passes through two observations, called two particular observations called as support vectors. Okay, so support vectors are the observations which are very closer to the bound decision boundary. Okay, so if we draw two lines passing through these two support vectors, then we can find out the decision boundary as an average for it. Okay, so we have to maximize the margin while selecting the appropriate decision boundary. Okay, so these are called the hyperplane. This is the decision boundary is now called hyperplane, and these two observations are called support vectors. Okay, and we have to increase the marginal distance. So, let's see. In support vector machine, we are using a hyperplane to suppress two observations. So definitely, in this case, which one is the best hyperplane? A or B? A is the better hyperplane, even though B is having higher margin. A separates these two group of objects properly, right? Because B, there is a misclassification. So we have to choose the hyperplane A, which gives the proper classification, even if it is not having much marginal distance. Okay. Now in this case, see, is there any line which separates all the blue dots and blue stars and red dots? No. This is a point isolated, right? So what we will do is we will neglect points. Okay, we will neglect points which completely distracting the properties of the point 2. Okay, and we will neglect this and we will find out a hyperplane here. Okay, now what is the case of this? What is what is what will we do at this case? Because if the data is distributed like this, we will not be able to find a hyperplane, right? Is it possible to find a line here? Is it possible? Is it possible to find a hyperplane here? So what we will do is we will apply a particular type of method called a kernel trick. Okay, what we will do is, see here we have two features, right? Here we have two features, x and y. Okay, which represents the coordinates of these points. Okay, and I am introducing another point, z is equal to x square plus y square. Z is equal to x square plus y square. Then what will happen is, for all these red dots, okay, for all these red dots, the value of z will be higher, right? Sorry, lesser, right? And for all these blue dots, for all these blue stars, the value of z will be higher. Okay, so if you are converting this xy data into xyz, see, on the top view the data will be exactly like this, but on the side view you can see the value of z is higher for all blue dots and value of red is low for all red dots. So in two-dimensional it is not separable, but here in this case we can actually find a plane that separates these two classes, right? Okay, we can find out a plane like this. Okay, so if you draw a plane like this, all blue points will be on top of the plane and all red points will be on the bottom side of that plane. So that is how we can separate these two data. Okay, so this is called as a kernel trick in SVM. So SVM assumes that if a particular data is not linearly separable in a particular dimension, okay, if a data is not linearly separable in a particular dimension, it will be linearly separable at some other higher dimension. It will be linearly separable at some other higher dimension. Okay. Now I'm explaining it a bit faster because it is all same what we have done for the previous experiment. So we are loading the iris data set at the first block and printing it. Do you know what is iris data set? Iris data set is it's nothing but it's a CSV file representing the features of a particular type of flower called iris. Okay, it some experiments with iris data set is actually very what very common in while learning the data mining and machine learning process. Okay, so iris data set is a data represents the different features like sepal length, sepal width, petal length, and petal width of iris flowers. And according to these values, okay, on different range of these values, the species of iris will change from setosa, virginica, and versicolor. Okay, there are three different type of three categories of iris flowers: setosa, virginica, and versicolor. So our task is to create a classification model. Our task is to create a classification model for predicting the species of iris data. Okay, if you are having an iris flower and you have measured the sepal length, sepal width, petal length, and petal width, then if you are giving these features as input, the system should predict whether it is setosa, virginica, or versicolor. Okay, so see, we are plotting the data set. We are plotting the data set. Okay, using the features sepal length and sepal width. Okay, using the features sepal length and sepal width. Okay, so you can see the setosa observations are having high sepal width and low sepal length. Okay, and see the virginica is having high sepal length and on average sepal width. And for versicolor, it is in between the virginica and setosa. Okay, so with this information, we can actually, so this is only a two-dimensional representation because we are having four features, right? So the representation of four is not possible in a two-dimensional plane. That is why we are just only taking the sepal length and sepal width. You can also plot with petal length and petal width. This also makes sense. See, for petal length and petal width, the setosa is having low petal width and low petal width. The virginica is having high petal width and high petal length, and versicolor is in between this range. Okay, so they are linearly separable somehow, and this is a multi-class classification problem. Now what we have to do is we have to split the data into X and Y. That is all these columns, sepal length, sepal width, petal length, and petal width to X, and species as Y. Okay, so we have splitted that into X and Y. Okay, so we are printing it. You can see the X values are here and the Y values are here. Now the Y values is not numeric values; they are all categorical values. So what we have to do is what we have done before with the features, sex, and region in the previous use case. That is, we have to create a label encoder object and transform it into categorical values to numerical values. Okay. So now the Y values are 0, 1, and 2. That is, the setosa is represented by 0, the versicolor is represented by 1, and the last one is represented by virginia. Okay. Now, again, we are splitting X and Y into X train, X test, Y train, and Y test. We are printing that values to X train, X test, Y train, and Y test. Okay. Now the things are quite simple. First, we have to create the support vector classifier. For that, we have to import SVM from SVC from sklearn.svm From sklearn.svm, import SVC. From sklearn.matrices, import confusion matrix. Okay. Then create the object of SVC classifier. Then call the fit function xtrain and ytrain. Then call the score function with xtest and ytest. And you can see a particular type of matrix called confusion matrix that I will explain. You see, this is the confusion matrix represents the correctness of our model. So the first row and first column means the first category. That is, what is the first category? We have setosa, then versicolor and virginica. So from this matrix, you have to understand that we have taken 16 observations for setosa for the prediction. And among them, 16 are correctly predicted. 16 are correctly predicted to setosa itself. And in the second row, we have taken 18 observations of versicolor, 18 observations of versicolor, and 17 are predicted correctly as versicolor, but one is predicted as virginica. Okay, one is predicted as virginica. And the last case also, 11 observations of versicolor is taken for test because within this test, X test, 7 observations of versicolor is there, and 7 is actually predicted as versicolor itself. So we have only one error happened here, and the total accuracy for our model, okay, total accuracy for our model is actually, on printing this, you can see we have 97.97, that is 97%, or we can round it as 98% accuracy for our model. Okay, and the same problem, the same data is now training with the decision tree classifier. This is another type of classifier like support vector machine. So the difference is only here. We have to import decision tree instead of SVC here. See, and the object is now created as SVC. Here we have to create as decision tree. Everything else is same. Fit. Then find out the score. We can find out the score here. Then predict with X test. We will get Y pred, and we will print Y test and Y pred using a confusion matrix. Okay. So here also we get 97% accuracy. Either we can use a support vector classifier or a decision tree classifier. Okay. So this is what we have to do with the classification example. Hope you got the output. So I'm explaining it. I'm giving you a small brief regarding k-means clustering. Like we are having a several data points. First, we will randomly choose the cluster heads. Okay. Then we will calculate the distance from each cluster head to all the points. Then we will move the points according to the nearest cluster head. We will recalculate it. Again, we will find out the distance. Then again, we will move to some other clusters, and likewise, after several iterations, the entire data will be converged to some set of clusters. Okay. So here we have a data called mall customers. According to the data given in this mall customers dot CSV, we have to cluster them into several groups. Okay. So for that, first we are importing the data. Then we have to load the data and see this. We have the customer ID, gender, age, annual income, and spending score. Okay, spending score. Customer ID is just an ID. The gender is actually categorical value. Age is a numerical value. Annual income in dollars, and spending scores in dollars. Okay. Then you can print the shape of the data. It's around 200 rows and 5 columns. Okay. Now data set info, we will get the column names as well as the different, what are the types of each column, how many informations are there. So first we have to find out, is there any null value? So on observing this, we can see there is no null value at the data. Okay. Now, what we are going to do is what are the informations or what are the features are relevant for this particular type of clustering? Just think of it. Is customer ID a factor? No, right? Is gender maybe, and age maybe, but in our example, we are considering only the annual income and the spending score of the people or of the customers to categorize, to group them into several groups. So we are taking all the rows and only taking the third and fourth columns as the features. Okay. Now, one of the major challenge you will face while doing the k-means clustering is what is the actual value of k. So what we will do is we will perform clustering with different values of k. That is, we can calculate or we can perform the k-means clustering with k as I. I can be ranging from 1 to 10. Okay. Then we will find out a score called inertia, which represents the correctness of the clustering. If the inertia is very high, then we are getting a wrong clustering, and the same case happen if inertia is very low. So we have to take the average value for value of inertia. So we will try clustering with each of the value of I equal to 1, 2, 3, etc. up to 10, and we will fit the data and find out the inertia score. Okay. And now we are plotting it. Okay. On plotting it, what is the value apt for the inertia? Where is the sudden break you observe in this curve? The sudden break is happening at this 5, right? This point. Okay. So the correct value of or the appropriate value of k is actually 5. Okay. Now we will build a k-means model. After k-means model build on k-means model building, we have to specify the n cluster equal to 5. Then we have to use an initialization mechanism, which is an intelligent initialization mechanism, because to intelligently choose the first cluster head, because the entire correctness of the cluster head depends on the first cluster head. So to intelligently select the cluster head, we are using a initialization mechanism called k-means plus plus. Then we are using the fit and predict function to cluster it. So on printing this by k-means, printing this by k-means, you can see there are 5 clusters. Some observations in belongs to 4, some observations belongs to 3, some belongs to 1, some belongs to 0, some belongs to 2. Okay. So see, we are plotting our observations corresponding to each of the cluster value. So here the first cluster is plotted with blue color. For that, we are using a for loop for I in range of 5. The value of I can be 0 to 4. So on the first iteration, a scatter plot will be plotted where the kb is equal to 0. Okay, so it will get plotted with blue color, and on the second iteration, it will get plotted with orange, then green, then red, and violet. Okay, and finally, we are plotting another thing which is called the cluster centers. We can get the cluster centers by calling the function, by calling the property cluster center from the k-means object. So we are plotting it also. Okay, so you can see the cluster centers of each of the cluster, and there will be a title, a label, and by label the legends is to show this, and plot.show function will display the image. Okay. So finally, we can see which are the clusters formed. Okay. So this is the implementation of a k-means clustering. So you might learn about other clustering techniques in the previous lecture. So you can apply those clustering techniques for performing this instead of k-means. Okay. So hope you got the files with you, so you can try out with other clustering techniques too. Okay. So that's all for the today's session. Now it is open for the question answering part. If you have any doubts or if you need any clarifications, you can ask. Okay.
Thank you so much, sir.
Yeah. Thank you.